Hey guys, how you doing? This is a video lecture on 11.1, a kind of an overview of chapter 11. So chapter 11 is a pretty dense chapter as far as information, and it's really front-loaded. Most of the really important conceptual stuff you have to know is in section 1, and then section 2, 3, and 4. They go over more of the details of significance tests, but there's some stuff there that I would consider a little bit extraneous. So in my lectures, my goal is to really highlight what's the most important things, and there's two sort of things that I need you to focus on. The one thing is the conceptual understanding. That's what we're going to talk about today. The conceptual understanding meaning like what is the big idea of significance tests? What is the thinking? Like what is the thinking behind significance tests? That's something that you really have to understand. There's a couple sort of catchphrases that I'm going to have you kind of memorize because those catchphrases will help you understand the concepts behind significance tests. Then, on the other hand, on the other side, the thing that I'm going to talk about later on is the procedures, right? Just mastering the procedures of significance tests for all the different scenarios that we have, right? And we're going to start off with the most simple significance test, a test for mu, and a test for p, right? So kind of like carrying on what we learned about confidence intervals. Okay, but before we get to the procedures, we have to clarify the thinking behind the tests. Okay, so after this lesson, you'll be able to state correct hypotheses. So H null and HA, or the null hypothesis and the alternative hypothesis for a significance test about a population proportion or a mean. Okay. Interpret p-values in context and interpret a type 1 and type 2 error in context and give the consequences of each. The consequences aren't always going to be immediately clear. It's something you have to kind of think about, and there's definitely some maybe a little bit of assumption that happens in the consequences. Also, you have to understand power, and so the relationship between the probability of a type 2 error and just the significance level of a test. Okay, so here we go. So we learned all about confidence intervals, and confidence intervals, it turns out, are a very strong, very valuable tool because the big idea of a confidence interval is that you're estimating a parameter, right? You're estimating something about the entire population. So the two parameters that we estimated so far are p and mu, okay? And so when you construct a confidence interval, you go through this pretty rigid process, these steps, right, of checking conditions, state plan, do, conclude, right, using the right degrees of freedom if it's t distribution, figuring out if it's a t or a z distribution, thinking about the sampling distribution. You go through all of this, these sort of rigid procedural steps, and then it produces something very valuable. It produces a range of plausible values, a range of believable values that will capture the true parameter that you're searching for, C percent of the time, right? C level percent of the time, right? So that's a very valuable tool. So now we're going to do what's called a significance test. Okay. The significance test is also a helpful tool. It's a valuable tool, but maybe not quite as valuable as a confidence interval. Okay. So the big idea behind a significance test is whereas with a confidence interval, you wanted to estimate, a parameter, right, within a certain margin of error. Here, what we're doing is we're not going to estimate a parameter. We're going to find evidence from our one sample, and later on we'll do two samples in chapter 13. But in our one sample, we want to know, does that sample data provide convincing evidence against a claim, against a particular claim? And we started to kind of get you into inferential thinking or statistical test thinking when we asked you questions in the homework or on the assessments like, hey, construct a confidence interval, and does that confidence interval provide evidence for a particular claim, yes or no? And that's really what significance tests are all about. That's what the big idea of a significance test is it's to find evidence against a particular claim. That particular claim is called the H naught or the H null, okay, which is the null hypothesis. Okay. Okay, so this is sort of a phrase that I want you to write down, and I want you to kind of remember this, right? So in in quotation marks here, if we took many samples, and they're always random samples, we're going to sample properly, right? But if we took many samples, and if this claim were true, we would rarely get a result like this. Okay. Well, how rarely is what we want to know. And so there's actually a mathematical measure of how rarely, and that is all based on the laws of probability. And so that value is called a probability value or a p value. Okay. So here's our first hypothetical example. Let's say that there's a basketball player who claims to be an 80% free throw shooter, right? So we're kind of thinking in our mind, 80% free throw shooter, that's really high. We kind of are suspicious that maybe that's a little bit of an overstatement. Maybe this guy really is not an 80% free throw shooter. Maybe his true proportion of success for free throws is less than 80%, right? Less than 0.80. Okay. But the claim is that he's an 80% free throw shooter. So that's a P of zero point 0.8. So that is a true population proportion. So this basketball player is saying out of all the, free throws that I've taken, that I will take, I'm an 80%, I'll make 80% of them because I'm an 80% free throw shooter, right? So that's claiming that the true population proportion P equals 0.8. Okay. So we take him out to the free throw line and we give him a basketball and we say, here you go, prove it. Okay. And I shouldn't say prove it, but here you go. Let's gather some data. Okay. So let's consider this a random sample. Let's go ahead and shoot 50 shots, a random sample of size n equals 50. Well, he goes ahead and shoots 50 shots, and we count them, and he only makes 32 out of 50. Well, that's a problem because he claims that he's an 80% free throw shooter. So we would expect if you're an 80% free throw shooter, you wouldn't make more than 32 out of 50, right? You'd probably make like 40 out of 50, right? So what is 32 out of 50? Well, that's a p hat of 0.64. Well, is it possible that if this guy really is an 80% free throw shooter, is it possible that he could shoot 64%? Sure, of course it is. It's possible. But the question is, how likely is it? Okay. And really, the question of interest for all significance tests is how likely is it for us to get a sample result that is this strange or stranger if the null hypothesis is true? Okay, so that's a conditional, right? That's an if then. So given that the null hypothesis is true, so given that this guy really is a 80% free throw shooter, what is the likelihood or what's the probability of getting one sample result of this strange or stranger, meaning of 0.64 or worse, 0.64 or less, given that he really is an 80% free throw shooter? That is the big question of significance tests. Okay. So what we want to do is really look at the sampling distribution. We want to look at all possible samples of size n equals 50 for a person who really is an 80% free throw shooter. Now, that's not a finite population, that's an infinite population. So we can't get the actual sampling distribution, but what we can do is use computer software to simulate, 400 sets of size n equals 50. So 400 samples of size n equals 50. And we set in the computer software, we set that the true proportion of success, the true population proportion of success, P is equal to 0.8. Okay. So this computer software is going to give us some sampling variability, right? And now each one of these dots, there's 400 red dots. Each one of these one red dots is a different p hat. It's a different sample result of someone who is an 80% free throw shooter. Okay. And what is their sample result for n equals 50, right? What is their p hat for n equals 50? So most of the time, this person is shooting right around 80%. Okay, well, where is a p hat of 0.64? Well, out of 400 red dots, there's only 3 red dots out of 400 that are at 0.64 or worse. Remember, that is the big question of significance test. Given that the H null is true, given that given that this person really is an 80% free throw shooter, how strange is it, or how likely, what's the probability of getting a result, a sample result, this strange or stranger? Okay, so it's a left tail question in this case. Okay. So our H null, our null hypothesis, is a statement about the parameter of interest. It's a statement about the entire population. Okay. And I'll get to that in just a moment. Okay. So if this guy really is an 80% free throw shooter, okay, then, and he returned a sample result of p hat equals 0.64, that means that, yeah, okay, maybe this guy really is an 80% free throw shooter, but we just had a very unlucky day, right? The 3 out of 400 day, right? Okay. So either the claim is true, he is an 80% free throw shooter and we got very unlucky, or this could be strong evidence that, you know what, you're probably not an 80% free throw shooter. In other words, this could be evidence against the claim. Okay. So now here is the null and the alternative hypothesis. The null hypothesis is H naught or H null or H zero. Okay, this is not an O, it's not a letter, that's a zero. Okay, so the null hypothesis, this is worth writing down in your notes, is a statement of no difference, status quo. Okay, no difference. Okay, that means we accept the claim. No, we don't accept, let's scratch that word. That means this is the claim. Okay, that's being made. Okay, the original claim. So what was the original claim with the basketball problem? The guy was claiming that his P is equal to 0.8. That's the null hypothesis. Okay. The alternative hypothesis is kind of what our sneaking suspicion is. We think, no, you're probably less than an 80% free throw shooter. And these are set before we gather any data. Okay, so H null and HA. H null is a statement that P is equal to 0.8. HA, the alternative hypothesis, is that P is less than 0.8. Okay, this is exactly how you're going to write your null and alternative hypothesis. Yes, you're going to stack them one on top of each other. Yes, you're going to have the colon. Yes, you're going to have subscript 0, subscript A. And yes, you are going to have parameter is equal to some value. Parameter, never statistic. Okay, that is worth writing in your notes. The hypotheses are statements about the entire population. They're statements about parameters. Never, never, never write statements about statistics in your hypotheses. So what does that mean? If you were to write H null P hat equals 0.80, that would get an instant 0 on that FRQ for the AP exam. Okay. Or if you were to write H null X bar equals whatever, that would get an instant 0. Okay. So do not write anything about statistics, anything about the sample in your hypotheses. Why? Because we don't have to hypothesize about our samples. Our samples are real data that we actually gather. We know what p hat is. We don't have to hypothesize what it is. We know what X bar is. Okay, we don't have to hypothesize what X bar is. Okay. Just like in our confidence interval, we know the statistics and we use those to make a statement, an inferential statement about the parameter. Okay, very important. Okay. HA, this is always going to be a statement that your parameter is an inequality, either less than, greater than, or not equal to, okay, some other value. Okay, these two values do not have to be identical, by the way. They can be different, okay? So P is equal to 0.8, okay, P is less than 0.8, or P is long run proportion of made free throws. Again, 3 different alternative hypotheses we can have, okay? So there's one-sided or one-tailed tests and two-sided or two-tailed tests. A not equal to is a two-tailed test or a two-sided test because this is just saying your parameter is different from your value. So it could be greater than or it could be less than. So you have to basically, you're checking 2 probabilities here. Okay, and how you actually do this is you just check one of those probabilities, then you just double it. Okay, you just double it. This, okay, I just blocked it. But that at the very bottom is never correct. Never write a statement in your hypotheses about statistics. Okay, that would be an instant zero for that entire FRQ. Okay, so never write about statistics. You're always inferring about parameters. So here's an example. So does the job satisfaction of assembly line workers differ when their work is machine-paced rather than self-paced? So one study chose n equals 18 subjects at random, so it meets the random condition. Okay, from a company with over 200 workers, so that's your capital N equals 200, okay, who assembled electronic devices. Half of the workers were assigned at random to each of two groups. Both groups, okay, so they're assigned randomly to different groups. So this sounds like an experiment, right? So both groups did similar assembly work, but one group was allowed to pace themselves while the other group used an assembly line that moved at a fixed pace. After 2 weeks, all the workers took a test of job satisfaction. Then they switched work setups. Excuse me. And they were tested again. The response variable is the difference in satisfaction scores, self-paced minus machine-paced. Notice that order matters. Self-paced minus machine-paced. So obviously a positive value, a positive difference means that self-paced is greater than machine-paced, means they prefer self-paced over machine-paced. Okay, what is the parameter of interest? What are we trying to infer about? Okay, what are we doing inference about? Notice that this is a matched pairs designed experiment. Excuse me. And the parameter of interest is the mean of the differences in job satisfaction score. Notice that order matters. Self-paced minus machine-paced. What would the two hypotheses be? Well, your null hypothesis is always a statement of no difference. No difference. If there's no difference, what would the parameter be? 0. Okay, sorry about that. Yeah, so literally the mu would be 0, right? Because the mu is the difference. And then the alternative is we don't know like whether this is a left tail or right tail. So this is a two-tailed. Okay, this is a statement of mu is not equal to 0. So the null hypothesis, H null or H naught, that is the claim. That's the statement of no difference. That's the claim that we are actually trying to find evidence against the null hypothesis. Okay, so that probability that measures the strength of the evidence against a null hypothesis is called the p-value. So a very, very small p-value, okay, is strong evidence against H null. Okay, a small p-value is strong evidence against H null. So what is p-value? What the heck is p-value? It's this. It's the probability, assuming that H null is true, of getting a sample result that would take a value this extreme or more extreme than the one that we observe. Okay, it's the probability, the likelihood, more than the likelihood, it's the mathematical probability of getting a sample result this strange or stranger given that the H null is true. That is what the p-value is. That is what it measures. Okay, small p-values are strong evidence against H null because they say that the observed result is unlikely to occur. It would not occur very, very often. Like if you get a p-value of 1%, that means that if H null is true, you would get a sample result of whatever your sample result is only 1% of the time. Okay, only 1% of the time. Okay, large p-values fail to give evidence, convincing evidence against H null. So if you get a p-value of like 23%, well, what does that tell you? That means that if the null hypothesis is true, you would get a sample result of this, of this amount, like this far away from the true, center. Okay, this strange or stranger about 23% of the time. So that is not very unusual. That's not, strong enough evidence for us to say, we doubt the H null. We doubt your claim. Okay. All right. So there's our null hypotheses. So data, so now we're actually getting the data. So now we're getting the sample summary statistics, right? So n equals 18. We got an X bar of 17 and a sample standard deviation of 60. That is, these workers rated the self-paced environment on average 17 points higher, right? Because it's self-paced minus machine-paced. So they tend to, it seems like it seems like maybe they like the self-paced more. But researchers performed a significance test using the sample data and found a p-value of 0.2302. 23%. Okay. So what would it mean if the null hypothesis was actually true, if mu equals 0? What does that mean? Well, in this setting, what that means is that there's no difference. People don't care, about self-paced minus machine-paced. There's no big difference, right, in this parameter, right? So if self-paced minus machine-paced is 0, that means there's no real preference, right? And think about on the quiz, the Starbucks minus Pete's, right? They rated Starbucks, they rated Pete's. If that difference was equal to 0 on average, that means that teachers really don't care. Like they don't have a preference of Starbucks or Pete's, right? So that's what mu equals 0 means in this context. Okay. So now let's interpret the p-value in context. This is worth writing down. An outcome that would occur so often just by chance, okay, almost 1 in every 4 random samples, right? 23% is close to 25%. When H null is true, is not convincing evidence against H null. So we reject, or do we fail to reject H null? We fail to reject. Okay, so those are your two answers. When you do a significance test, your two answers are either going to be we reject or we fail to reject. Okay, we never say that we accept H null. Okay, and even worse than that, if you say we accept H null, you'll get huge points deducted. But worse than that would be this: if you said the statement, "Oh, this proves that there's no difference." If you use the word "proves," you'll get an instant 0 on the entire FRQ. Why? Because significance tests don't prove anything. Okay. They don't prove anything. They just provide evidence for or against the null hypothesis. Okay. The final step in forming a significance test is to draw a conclusion about H null and about HA. Okay. So again, you either reject or you fail to reject H null. If our sample result is too unlikely to have happened by chance alone, assuming H null is true, then we'll reject H null. Otherwise, we fail to reject H null. So that begs the question, well, how weird does our p-value have to be? Like how small does p-value have to be to reject H null or to fail to reject? Well, there is a threshold value, and that is called your alpha level. Okay. There you have it in a nutshell. Okay, I'm going to pause this video, or I'm going to stop this video. I'll talk more about alpha levels, beta, type 1, type 2 errors, all the rest of that in the next video. Thanks, guys.